Okay, in the last video we looked at the derivation for d sine theta is equal to m lambda for a pair of double slits. There's another one you can actually use with that situation though. And that one is that delta y is equal to lambda L on D. Now delta y is the fringe separation, the distance between any consecutive pair of bright fringes there. L is the length as we've done before, D is the distance between the slits. So you've already got a formula here for that. D sine theta is equal to m lambda. Now if you check this on a calculator, these angles are normally about 1 degree, so not very big. So the sine of 1 degree is a very small number, down to 5, 6 significant figures. You'll find that the tangent of that is virtually the same. So you can replace d sine theta with d tan theta. So just try that on a calculator for yourself and just see how close those two are. Very, very close. All right, you have to go down about the 4th or 5th decimal place before you see a change in that number. So we can actually substitute d sine theta for d tan theta. Now the tangent of theta here actually has a relationship for this triangle here. Okay? Because if you check it, you've got an angle and we've got delta y here in that side and we've got L as that side. So the tangent of theta is actually delta y over L. Now the m value here is 0 to 1. So we're only talking about 1 for the m value. So we can actually replace that with a 1 or 1 lambda. So based on that here, you should find a formula that you can rearrange now. So the actual value will be delta y equals lambda L over D. So that's a lot easier to work with because you can see there that if you've got something where you move the screen further away and you move the screen further back, you're going to get an increase in the fringe separation. They're going to spread out because they move further back. If you use a bigger wavelength, you're going to get a bigger fringe separation. If you make the slits closer together, again you're going to get a bigger slit separation because as that goes down, this one's going to go up because they're inversely proportional. So it's a very useful formula to use. Now you can obviously measure the fringe separation. If you were told the slit separation and the distance to the screen, you could find the unknown wavelengths for certain light sources that you put there. So that's one of the uses of it. So this is the alternative formula. You do not need to know the derivation, but you can go from there. Okay, so we've now got this formula that will tell us the fringe separation for a certain double slit pair. And don't forget you've actually got the idea of being able to sketch the intensity graph or draw the pattern or describe the pattern or explain why the pattern is produced. So what would it change if we actually changed to multiple slits here and had lots of them? Now these multiple slits, we're talking about maybe something with 600 lines per millimetre as a grating there. So this is something that's been scratched on there like this, where you've got some glass and you've actually scratched on here lines that are actually only 1/600th of a millimetre apart. Okay, so they're really close together and the slits themselves are very fine, okay, very narrow. Now because of that, first of all, because the slits are narrow, we're going to get very good diffraction around that in several directions, all right, up to 90 degrees in either direction, okay? And so you're going to get good spreading of the light because of the diffraction because the slits are very, very narrow. But not only that, the slits are also really close together here. This distance D is extremely close, okay? So you'll find the pattern spreads really wide as well, and it's a long way between the first maxima here that you might get, this one here, and the next one's a long way away. Okay, so it's not over only 1 or 2 degrees at the most, it's over a big spread of angles. So the diffraction is going to spread it very well and spread the intensity quite well. If you think about the double slit pattern, when the distance between the slits is very close, the actual fringe separation was very big. And the same thing is going to happen here. For very, very close together ones, they're going to be a long way apart between maxima. So what you get for a multiple slit pattern or diffraction grating, a very sharp, narrow maxima, like this, very intense, and they'll be much further apart like that, to much larger angles. And the next one's not actually the same distance. This actually gets bigger as you go across. So this actually gets greater, so I'm not drawing it to scale very well. And you can use a derivation to get the same sort of formula as before. And in actual fact, it's an easier one. So if we start to draw these going out to imaginary point P out there, it turns out that because these are so close together, you can draw these as parallel lines, and there is your path difference there at 90 degrees. And so the same argument can be used to show that that x is the path difference, and it's equal to d sine theta, where the 90 is in that little triangle there, like that, and this is theta. So you don't have to do as much in terms of approximations now. So for constructive interference, when we're going to get a bright spot here at point P, it's going to occur when that path difference is a whole number of wavelengths again. So you can use virtually the same argument. Now if that happens then, that slit there will be in phase with the one above it, and arrive in phase and give you constructive. And also the second slit up and the third slit up, all of those will be in phase with the one below it by having a path difference there of one wavelength to the first order. If you go to the second order, m equals 2, it's going to occur when the path difference between each of these is 2 lambda and 2 lambda. But again, they're all going to arrive in phase and give you constructive interference. So it's a very similar formula you can use. All right? Now this is a more typical question to use for the d sine theta 1 equals m lambda, because you've got much bigger angles and it's an easier measurement to do with those large sizes. So a typical question you might get will be along the lines of, find the angle to the first order maximum, or the third order maximum, so third order maximum. In which case you're going to gain, there's m equals 0, m equals 1, and m equals 2, and m equals 3 will be much further up, it'll be up here somewhere. Okay? And you're going to be using your d sine theta formula equals m lambda. Just be aware then, you need to work out the distance between the slits. So they tell you that it was 600 lines per millimetre on a diffraction grating. You need to work out how far is it between those pair of slits in there. Now there's a formula on the formula sheet, d equals 1 over n, where n is the number of slits, or number of lines per millimetre. So you'll be doing 1 over 600 here. But you must get this into metres. If it's got 600 lines in a millimetre, it'd have another 1,000 times that in a metre. Okay, so you've got to times that by 10 to the 3 to get this into metres, that milli value there. So that's the sort of value you're going to get. And I think that's going to be 1.67 by 10 to the minus 6 metres. It's a very close distance there. If you substitute that in and rearrange for theta, you can get that then and work out what the order is. Okay. Now, something to be conscious of with diffraction gratings there is that you can't use this formula delta y equals lambda L and D, because that's based on an approximation that the sine of theta is approximately the same as tan theta at those small angles of 1 degree or 2 degrees at the most, whereas we could be dealing with angles here of 30, 40, 50 up to 90 degrees. So because of that, do not use this formula in the diffraction grating one. Okay? So that's the sort of thing you're going to get if you pass a laser through a diffraction grating. You're going to get your zero order and then a first order on each side, and the second order is going to go further out. And the derivation of that is very similar to your one with a double slit, except you do not have to approximate this idea here of 90 and theta there. So once you've shown that the x value in here, the path difference is d sine theta, we can say that's going to be a whole number of wavelengths for each slit to be in phase when it arrives with the slit above it. Okay. Now, you will get negligible intensity between the maxima. They're really sharp, these here. So those maxima are much sharper. They don't go down steadily, then go up steadily like in the double slit pattern. All right. Now the reason for that is if you are just fractionally out the perfect value, say you actually sort of, instead of being a path difference of 0, you are just a path difference of 100th of a wavelength out. What would happen is, for this first slit here, you would find a corresponding slit 50 slits further down to the 51st slit, which is 50 of these away. So 50 hundredths out, which is a half a wavelength. And being a half a wavelength out means that you're going to get destructive interference. So this first one will be out of phase with the 51st one. The second one will be out of phase with the 52nd one, and so on. So each one of the top half of the grating, if you like, has actually got a corresponding slit further down that is perfectly out of phase with it. So you get very little intensity as soon as you go off that exact value of a whole wavelength, or 2 whole wavelengths, or 3 whole wavelengths between each consecutive pair of slits. Okay, and so that's why you get this sort of very weak maxima down here. Okay, it's a very hard question to answer that. It's very rare they ask you that. All right. Now we've already got this idea here about what to do if you've got a diffraction grating there that I've just gone through. You can work out your distance between the slits, work it out, and rearrange for theta, and you'll get an angle. And you can see it's much bigger than what we've been doing with double slits. If you ask what is the highest order maximum possible and how many maxima can be seen, that's going to be theoretically anything less than 90. Okay, so if you put theta equals 90 in there, the sine of 90 is 1, and you should be able to put your other values in and work out what's the total maximum you can get. Because here it turns out to be 7.7, which means your maximum is going to be 7 as your highest order, which means you're going to get 7 on each side and 1 in the middle. You could get theoretically 15 maxima there if they're bright enough to see. Okay. Now what happens if you put white light through there? If you put white light through here, you've got to remember that the sine of theta is proportional to the wavelength. Sine of theta is proportional to wavelength. And for white light, we've got a whole range of wavelengths from red and going all the way down to violet, okay? And that range of wavelengths starts with the big one and goes down to the very small one, okay? So if you imagine sort of red light first of all, it's got a large wavelength there, it's going to go to a larger sine angle or a larger angle. So it's out here somewhere, okay? Obviously each wavelength alongside that is slightly smaller, so the angle's smaller. So you'll get a perfect spectrum here from red all the way through to violet, Roy G. Biv in reverse, okay? And that's because the maxima are sharp, and for each wavelength you get a different angle there. In the middle you'll get white light because all of them are at a maxima here. So here you get a first order spectrum. The second order spectrum is in the same order but it's much more spread. And it turns out that the third order angle for blue is slightly smaller than the second order angle for red. So there's an overlapping of the pattern there. Alright, so you'll find you get a magenta sort of colour in there or a dark pink. But that's where you'll get if white light goes through. So you've got some notes on that as well, if you check through there. There's the why is the spectrum produced when white light is used, and the key things to point out is that the white light is made of different wavelengths and the sine of the angle is proportional to those wavelengths, so the angles are different for each wavelength, and you're going to get a separation of colours, or a nice rainbow if you like, going from violet out towards red as you go away from the centre. The second and the third order overlap, okay? So you can think of it as being like this, okay? We'll look at this later on, how a spectrometer can be used to work out wavelength using a diffraction grating. Thank you.